All right, let's dive into one of the real workhorses of machine learning, logistic regression. Now, I know the name might sound a little heavy, but trust me, it's an incredibly powerful tool that solves a very common problem. By the end of this, you'll totally get it. So let's jump right in. So let's start with the basic problem we're trying to solve. Machine learning is amazing at predicting numbers. We can forecast sales, we can estimate temperatures. That's kind of old news, right? But what happens when the answer you're looking for isn't a number at all? Right, exactly. If you want to predict the price of a pumpkin, a model like linear regression can do that in its sleep. It just spits out a number. But what if your question is totally different? What if you want to know if that pumpkin is going to be orange or white? How does a machine predict a category, like a color? This is really where our story kicks off. And this slide just lays it out perfectly, doesn't it? Over on the left, you've got linear regression. That's our go-to for numbers, like the price. But on the right, you've got its clever cousin, logistic regression, which is built for one specific job, predicting categories, like our pumpkin's color. They're two different tools for two very different kinds of problems. Okay, so here's something that trips a lot of people up, and I want to get it out of the way right now. That name, logistic regression, it's honestly a little misleading. It's got regression right there in the name, which we just said is for predicting numbers. But its real job is something else entirely. And boom, there it is. The absolute key insight. Logistic regression is a classification method. Its job isn't to predict some value on a sliding scale. Its job is to put something into a box, to assign it to a specific category. It's a classifier, plain and simple. If you can just lock that idea in your head, everything else is going to fall right into place. So if it's not a normal regression, how in the world does it pull off this classification magic? What's the secret sauce that lets it pick a category instead of a number? Well, it's actually this really elegant two-step process. So believe it or not, it all starts in a place that's super familiar, a good old linear equation, just like we'd use to predict a price. That first step takes all our inputs, things like price, size, maybe the month, and it calculates a score. But here's the cool part. In step 2, it takes that score and runs it through this special mathematical function. And that special function is called the sigmoid function. The S-shaped curve you see here is everything. Think of it like a universal compressor for numbers. It can take any score the linear equation gives it, whether it's huge, tiny, positive, or negative, and it squeezes it, it forces it down until it has to fit somewhere on a scale between 0 and 1. That's the whole trick. So, why is a number between 0 and 1 so incredibly useful? Because we can treat it as a probability. All of a sudden, our model isn't just giving us a score, it's telling us the likelihood that something belongs to a certain class. An output of 0.8 isn't just a number anymore. It's the model telling us there's an 80% chance our pumpkin is orange. See how cool that is? Okay, so we have a probability. Now we just need to make a final call. We need a cutoff point, a line in the sand. And that's our decision threshold. Typically, it's just set right in the middle at 0.5. If the probability is higher than that, we'll classify it as white. If it's lower, we'll call it orange. It's that simple rule that turns a probability into a definite answer. All right, enough theory. Let's see how this all snaps together with a real-world example. It's time to go back to the pumpkin patch. So imagine we've got a whole bunch of data on pumpkins. And as we're looking through it, we start to notice a pattern. Generally speaking, the less expensive pumpkins, well, they're the orange ones. And then, as the price starts to climb, a different pattern emerges. The pricier pumpkins are almost always the white ones. So we have a pretty clear relationship here, right? Price seems to be a decent predictor of the pumpkin's color, which is the category we're trying to figure out. And this is where the logistic regression model just shines. Its entire job is to figure out the perfect S-curve that does the best job of separating our orange pumpkins from our white pumpkins. And remember that linear equation from step 1? The numbers in that equation are what the model actually learns. They control the location of this curve, like the exact price point where the probability flips from orange to white, and its steepness, which is how quickly that change happens. That's what it means to find the best fit. Now this is all perfect for a simple binary choice, orange or white. But let's be real, the world is usually more complicated than that. What if we have more than just two options? Well, turns out, logistic regression is way more flexible than you might think. There are actually a few different flavors. We've been talking about binary logistic regression, which handles two classes. But there's also multinomial, which you use when you have more than two categories that don't have a natural order, like orange, white, and striped. And then you have ordinal, which is perfect for when your categories do have a clear sequence, like small, medium, and large. So as you can see, logistic regression is so much more than just a statistical formula. It's a new way to ask questions about the world around us. It gives us the power to teach machines how to classify information, which is used for everything from filtering your spam emails to helping doctors make medical diagnoses. The big takeaway is this: you now have a real foundational sense of how to teach a computer to make a choice. And the only question left is, what choices will you teach it to make?